of the Learning Glass Studio, where we will talk about an aspect of manufacturing that has pretty much dominated the world of cheap parts and mass-produced parts. It's injection molding, where you inject the molten plastic to make a plastic part. And specifically, we'll talk about a remote control, how to make one of those. So you can imagine you have a remote control for your Fire Stick, something like this. On that dimension, and then from the side, it's composed of two halves of the shell, and the button, like something like that. And for this particular design, it's going to be on this dimension 5 centimeters wide, and then on this dimension 16 centimeters long. And then the shell doesn't show it how thick these walls are, but let's say that it's 2 millimeters thick. So that's a typical plastic part. This remote control, it will be some thin walls forming a housing for some electronics inside. So we're going to talk about the housing that's made by injection molding. And as we have been reading, that there's a lot going on here. We have to fill the mold, we have to dry the part, and so forth. And there's a lot of geometry in terms of the part you would want. So we'll analyze this as a simple example. So for example, if we're doing this injection molding, and let's say we want to inject this at a typical time scale, let's say this injection time of just flowing the molten metal in of 100 milliseconds or 1 second. T injection . 100 milliseconds. What is an estimate of the minimum pressure you would have to apply, or the delta P? Minimum delta P for injection, assuming that you don't inject from one hole, but you inject from a hole, the whole edge, from the over the entire width for injection across the whole width, and only for the top shell part, this part here. Not the bottom, and not the buttons. We'll ignore this outlet for this hole that we need to fit the button in, and there might be a battery hatch here. Not that, just this top shell. Okay, so let's analyze that, and this is very complex because it's a curvy part. There might be a lot of details in this texture that Jeff Bezos may have designed. There's this hole here that you have to fit buttons and probably more, a little logo there. And so that's how the real part would be. And we're going to simplify it in our analysis. So we're going to first analyze this injection process, which involves having a molten hot plastic that flows and injecting it into a mold that takes on this shape. And this part is a fluid mechanics problem. And the fluid mechanics is complex because the molten plastic does not behave in the simplest form of fluid mechanics. So it's a non-Newtonian fluid, but before we talk about that, another thing to note is that, I guess this makes it simpler, that it's a high flow rate. So we want to have a high production rate, so we want to increase the speed as fast as we can. That's good. And if we go too slow, another reason is besides a low production rate, if we go too slow, the metal might freeze, solidify before it fills the whole mold. That's another constraint in this design. So it's high flow velocity. It moves fast, but also these melts are typically high viscosity. You know, it's thick, so it resists deformation. That's one way of describing viscosity. So that means the viscosity actually wins, meaning that it's still laminar. So even though it moves really fast, it's still a laminar flow because the viscosity wins. So it'll be something like RE, some L over the distance times the velocity U over viscosity, something like that. It's the viscosity wins. Even though this is fast, this is bigger. So it doesn't go into a turbulent flow. That's one thing. And then the actual molten melt of the plastic is a non-Newtonian fluid. So molten plastic is a non-Newtonian fluid, which means that the viscosity changes depending on the forces you apply on it. Specifically, in this case, the viscosity decreases as the shear strain rate increases, which is the measure of how the velocity changes in, if the flow is going this way, would be the x-axis, say. The y-axis would be normal to that, and this variation in the velocity with respect to y is this shear strain rate, and this is non-Newtonian because it changes. And so let's look at a Newtonian fluid. So for Newtonian fluid in a channel, which is a classical fluid mechanics problem, we hopefully remember Newtonian fluid in an infinite channel. What that would look like was, here's your channel. There's the walls of the channel. And if we say that the velocity going this way is u, the velocity going this way is v, so this is x, this is y. We can say that for a typical viscous Newtonian fluid, because of the viscosity, the velocity is 0 at the walls because of the non-slip boundary condition. The velocity is 0, but if we draw a profile in this y direction, the peak velocity occurs somewhere in the center, and the walls are 0. So this would be the velocity profile. In the center, it's faster. Towards the edges, it's slower. So this would be the velocity profile as a function of position in the y direction. It also depends on whether it's fully developed or not. But when it's fully developed, in the ideal situation, it just maintains this shape and keeps on flowing at a given pressure drop. And another thing, so when this fluid is moving according to this profile, there's another parameter called the shear stress in this direction. And let's call that tau, the shear stress. So this would be the velocity profile. This would be the shear stress, and the behavior of this profile depends on the shear stress, and it depends on this gradient in space. So this derivative of the velocity with respect to position in the normal axis depends on the profile. That would be this gradient. So that's called the shear strain rate. So that's how a typical profile would look. And for a Newtonian, what makes this Newtonian is that you can write this relationship where the shear stress is equal to the constant velocity. It depends on temperature, but it does not depend on the shear stress as this does. So this would be, the shear strain rate. So this would be a shear stress. This would be viscosity. This would be shear strain rate. And this is Newtonian because does not change across this gradient. We see the shape of this profile changes shape, changes curvature. So this gradient would change, but the viscosity does not change because of that. It can change because of temperature, but that's a different story. It does not change because of the forces and the. So what this is, it's a resistance to deformation among the Y layers. So does not change with. And so what this is the resistance to deformation among shear layers, among Y layers, I meant. Shear strain rate. And that's proportional to the viscosity. Okay, so that's all a quick reminder of a more simple case where you can write this relationship to relate the shear stress in this flow. But when you have a non-Newtonian fluid, it's not, this viscosity also changes. But nonetheless, we can use our classical analysis to say that if we have a certain target time and we can estimate based on an analytical solution to this profile, we can find delta P. So let's do that. So for a target of T injection 0.1, there's an analytical solution to this viscous flow when it has this Newtonian behavior. It's a classical solution of the pressure drop is equal to this expression, this constant velocity in, it depends on temperature, but we're keeping temperature constant. That depends on the time that you have the time scale of the flow times the dimensions of your channel. So this is a classical analytical expression for Newtonian fluid in a channel. And so that's the first assumption we're going to make, is we're going to neglect, using this expression, the fact that we have this shear thinning. Did I write that? This is shear thinning. The viscosity decreases as the shear increases. So that's the shear thinning situation. We're neglecting that because we're saying it's constant with the profile. And if we apply this equation, we're assuming that we have a channel that goes infinitely in the width direction and that is flat. This remote is not flat. So nonetheless, let's use this. So the aspect ratio of this channel is the neglecting this 5 centimeters. What we're saying is that this channel is 16 centimeters long, and it takes 0.1 seconds to travel through it, and the distance from the channel is d. So that would give us, and then given also that assume we're given the dimensions of the channel by this estimation of the remote, we're specifying a target time of 0.1 seconds, and also that the mu of the melt is a constant at 40 PA seconds, Pascal seconds. That's a way to describe viscosity. Nice units, very easy to work with units. And we're assuming it's constant, which is a big assumption because this is not constant. It depends on where you are in the profile. Okay, so let's plug that in. So what we'll get is we have 12 times 40 Pascal seconds times 1 over 0.1 seconds times 16 over 0.2 squared. These are both centimeters. So that gives you a pressure drop, PA. So this seconds canceled out. So delta P minimum, it's minimum for, we'll talk about why it's minimum, is 30.7 megapascals equals 307 bars, which is a lot. The minimum is 307 bars. Right now, we're sitting in a room of 1 bar, 1 atmosphere. So we have to get the pressure 300 times bigger, a pressure difference, 300 times bigger than room ambient pressure, which is huge, but that's typical. And that's because it's viscous, highly viscous, and we want to inject it quickly with this short time. Okay? So why? So first we have shear thinning, the minimum. Why is this the minimum? It's an estimate. That's what we're asked to do, estimate it. So that's the estimate. But then can we say it's the minimum? It's because we simplified. All of these simplifications may mean that it could be bigger. Most of the reasons say that it's actually bigger. So with this equation, this classical Newtonian, solution is saying is that you're using a pressure difference between this end and that end to drive the mass to provide a net force from this direction to that direction, which will move the flow to the right. And it's using that pressure drop, and the only thing you're overcoming here is viscosity, friction in a way, the friction among the layers. That's what the force you overcome to go from here to there. So that's what we're applying here. But so there's more to this shape than that. So this P minimum, so this Newtonian channel flow only accounts for viscosity and which is friction forces of the fluid. But you might need more pressure to reach, needed to ensure all details of the mold are filled, because it's not flat. And to increase reproducibility, because the more like overpressure you have, the more it's going to fill it up, and if you overdo it, it's going to definitely fill it up. If you get at the right amount, there's going to be some error bar up and down. So increasing the pressure will help the quality. And of course, this shape is not flat and not infinite. So because it's not flat, you're going to have these features which might increase the pressure to get into that three-dimensional features. And because it's not infinite, it's not only the non-slip condition at the bottom wall and the top wall, you also have the non-slip condition on the side walls, which adds to this viscosity effects. Okay? That's why the pressure is going to increase for these two reasons. But conversely, because of shear thinning, if this slope gets more extreme, somehow this profile changes, then the viscosity will decrease. If it gets a sharper, so shear thinning for fast flow may decrease viscosity and reduce the pressure drop that's needed, because if it's less viscous, there's less resistance to deformation, and you need less pressure drop. So those are all details both in the geometry and the physics of the fluid, the properties of the fluid, which we did not account for in this very simple analysis. So that's an example of these actual injection molding processes. You either have to just by trial and error play with it or use some much more detailed analysis tools. And you can start from these rules of thumb and general simplified analysis, but there's more details, one of them, major of them being that this is a non-Newtonian fluid. Okay, so that's the injection time. The next question we'll ask is, once you inject it, you fill it up to its desired, you fill the mold at a high enough pressure, hoping that you get all the features and you fill it up without any drying, because that will cause problems in the material and the shape. The next question is, how long do you have to let it dry before you can move on to the next step, which is basically ejecting from the mold and putting a new, refilling and restarting the process. So the cooling time is a heat transfer problem. It's a material properties problem. So let's talk about that. And again, it's going to take account, it's not going to be completely accounting for all the complex competing processes going on. Okay, so for the cooling time, what is the cooling time? So if we're given that this mold operates with a molten temperature called T processing, let's say that temperature is 230 Celsius, T processing, and the temperature of that we wait until we can eject is called the ejection temperature. We let it cool to a temperature that reaches this, and then that's when we eject it from the mold. Why? Because if it's too warm, the material is not solid, and it will either just be liquid or it will deform. The ejection process will change the shape if it's not hard enough. Let's say that is 80 Celsius, and the mold that we keep at a controlled temperature is 60 degrees Celsius. So as we can imagine, these determine the time it takes to cool, meaning that if we need to keep it melted. This is the temperature that we keep the mold at. And we don't wait until the part reaches the temperature of the mold, because we can potentially speed up the process if we don't wait until that occurs. So that's a separate temperature called the ejection temperature, which would be like the minimum, the maximum temperature you would wait for, because ideally you don't have to, the lower, so it starts off at this temperature, and if you wait until it reaches 60, that'll take a much longer time than if you wait until it gets into an intermediate temperature. So the question becomes, what is the maximum intermediate temperature I can do before it causes problems? One problem would be if it's too warm, the material is too soft, And when you eject it using ejection pins most of the time, those pins will cause problems on the part, either punch a hole in it or cause a deformation if it's too warm. And if warm is good because it takes less time to cool, but it's not ready to be ejected. So there's an optimum there. Okay, so we won't do the heat transfer problem, but you can pick, you can solve the energy equation, the heat transfer equation, for a flat plate again. So simplify this for a flat plate under these boundary conditions, reaching this final temperature with these boundaries, meaning the initial temperature. So it'll be an initial value problem. The initial value is that this melt is at 230, and the final temperature, final value is 80 degrees Celsius, given some boundary of 60 degrees Celsius. You can solve that energy transfer problem, and what you would get would be the cooling time to reach 230 to 80 is given by this expression here for a flat plate. The thickness of the plate divided by pi over 2 times the natural log this T processing minus the temperature of the mold, they call it TD, and the ejection temperature minus the temperature of the mold. So that ratio inside the natural log. So that would be the solution to the energy equation. And in this case, the material has a low thermal conductivity. Oh, this is not 2, this is alpha, yeah. There should be, it should be the thermal conductivity of the material over pi, and also given of the melt material. Let's say that it's a constant value of 75 times 10 to the negative 9 meters squared per second, which is a nice unit to work in. And instead of thermal conductivity, it's thermal diffusivity, which is this meter squared per second. And plugging all those in, we know the distance of this plate, we know the temperatures are given, so we can use this simplified estimate based on a flat plate. With solving this heat transfer, you get 20.6 seconds to cool. Okay. So that is a simplified analysis where in both cases we did not consider the complex geometry that many parts have. And for the injection pressure for this fast time, we simplified it by using this flat plate. And then we had this viscosity relationships, which we had to simplify. And the fact that you're injecting into some features and more viscosity. So that was the minimum pressure drop. Here, we're also doing a simplified analysis. We're saying that for this flat plate, solving these governing equations, you can estimate based on a simplified expression for the energy equation, given these processing temperatures and the ejection temperature. So it gives us a ballpark of around 20 seconds. So in material properties, the thermal diffusivity changes slightly between a liquid and a solid. So that would not be necessarily constant when you're changing the phase. And depending on, you can play with these parameters here, that if you had a larger ejection temperature, you would have a bigger difference here, and that would make this number smaller here, and you would have a lower cooling temperature here. But as we said, if this is too warm, the part might deform when you try to punch it out of the mold. So even with this simple analysis, we can get a feel for the time scales and the forces required. You need a super high force to punch this super viscous fluid into the mold quickly, and you have to wait on the order of seconds for this material to be able to eject. Okay, so that's one quick example of how to analyze these injection molding steps. In real life, you would need much more detailed tools to account for this shear thinning, to account for the geometry, and to account for other material properties that might change. Okay, so that's all I want to talk about today. See you next time. Thank you.